All right, let's get right into it. Today, we're going to pull back the curtain on a really powerful technique, one that can take some of the most intimidating coding interview questions and turn them into something, well, surprisingly simple. This is what I like to call a coder's secret weapon, binary search on the answer.
So think about it for a second. What kind of pattern really separates a good interview performance from a truly great one at places like Google, Meta, or Amazon? It's usually not about memorizing more algorithms. It's about seeing the ones you already know in a totally new light. And the technique we're covering today is exactly that. It's a clever twist on a fundamental concept that can honestly make all the difference. Here's our game plan. First, we'll define what this secret weapon actually is. Then we'll get into the mindset of searching for the answer itself. We'll test it out on a simple problem, calculating a square root, before unleashing it on a classic, tricky interview puzzle about allocating books. And finally, I'll give you a playbook so you can spot these problems in the wild.
Okay, so first up, searching for the answer. This is where we need to kind of rewire our brains a little bit. We're going to stop thinking about binary search as just a way to find a number in a list and start seeing it as a tool for finding the best possible answer to the entire problem.
This slide really nails the difference. On the left, you've got the classic binary search we all learned. Its job is to find a specific value inside a sorted array. Simple enough. But on the right, binary search on the answer has a totally different goal. We're trying to find the optimal answer itself, somewhere in a range of all possible answers. We're not searching in an array anymore. We're searching in the whole solution space. So, what's the magic trick that lets us do this? Well, it all comes down to one crucial property: monotonicity. The best way to think about it is like this. If a bridge can hold a 10-ton truck, it can definitely hold a 5-ton truck, right? That's a monotonic property. If some potential answer X works for our problem, then any easier or less constrained answer must also work. That simple logic is the key that unlocks this entire pattern.
And here's the blueprint. It's really just a loop. Step 1, you figure out your search space. What's the lowest and highest possible answer this problem could ever have? Then you just pick a point in the middle. Step 3 is the big one. You check if that middle point is even a possible solution. If it is, great. As step 4 shows, you then try to find an even better answer by shrinking your search space. If it's not possible, well, your guess was off, and you shrink the space from the other direction. You just keep doing that over and over until you've cornered the best possible answer. Now that we've got the theory down, let's actually put it to the test. We'll start with a pretty straightforward problem, just to build up our intuition and get comfortable with this new way of thinking. So the problem is simple. Find the integer square root of a number, let's say 48, but you're not allowed to use the built-in square root function. Now you could do it the brute force way, check 1 times 1, then 2 times 2, 3 times 3, all the way up. But yeah, we can do way, way better than that.
So where's that monotonic property we talked about? Well, think about it. If we pick a number, say 6, and we check if 6 times 6 is less than or equal to 48, and it is, what does that automatically tell us? It means that 5 times 5, 4 times 4, and every number smaller than 6 will also definitely be less than or equal to 48. See? That's our monotonic property, and it's the green light to use this pattern.
Okay, let's actually trace this out for the square root of 48. Our search space for the answer starts at 1 and goes all the way to 48. Our first guess, the middle, is 24. Well, 24 squared is 576, way too big. So we can immediately eliminate the entire upper half of our search space. Our new high is 23. Let's do it again. The new middle is 12, still too big. Space shrinks again. Then we hit 6. Now 6 squared is 36, which is less than 48. So this is a possible answer. We'll hang on to it. But maybe we can do better. So now we search for a larger root between 7 and 11. By just repeating this process of guessing and shrinking, we super quickly zero in on the best possible integer answer, 6. And what's the result of all this? Instead of a linear search that checks every single number, we find our answer in logarithmic time. For a giant number like a billion, that's literally the difference between a few dozen checks and a billion checks. It's insanely efficient, and we didn't even need any extra memory to do it. All right, warm-up's over. Let's take this pattern and apply it to a much tougher problem, one you might actually see in a real interview: the infamous book allocation puzzle.
Okay, the problem goes like this. We have a bunch of books, each with a different number of pages. We also have a certain number of students. Our job is to hand out all the books in a way that's as fair as possible. And fair means we want to minimize the workload of the student who gets stuck with the most pages. We're looking for the smallest possible value for max pages any single student reads. It's a classic optimization problem.
So here's where we have to take that big mental leap. There's no sorted array of numbers here. So what are we searching for? Well, we're searching for the answer itself. We are literally doing a binary search on all the possible values that maximum pages could be.
The entire solution hinges on a clever helper function. Let's call it isPossible. This function takes just one number, our guess, our mid, and it returns a simple true or false. It answers one question. Is it physically possible to assign all these books so that not a single student ends up with more pages than this limit? That's our validity check.
And now we just apply our pattern. Our search space for the answer, the lowest it could be is the size of the biggest single book, and the highest is the sum of all pages. We pick a mid value. Then we ask our helper function, is possible mid? If it says true, awesome. That means this page limit works. It's a valid answer. So we save it and try for an even better lower limit by setting high equals mid minus 1. But if it says false, our limit was too strict. We have to let students read more. So we set low equals mid plus 1.
Let's wrap this all up in our final section, your playbook. This is what you need to remember to spot this pattern and nail the solution when you're in an interview and the pressure is on.
So how do you know when to use this? You look for these signals. First, is the problem asking you to find a minimum or maximum optimal value? That's a huge red flag. Second, can you define a clear range for the answer? And here's the absolute biggest giveaway. Can you imagine writing a function that just takes a guess, x, and tells you, yes, this is possible, or no, it's not? If you can answer yes to those, and that check is monotonic, you've almost certainly found a binary search on the answer problem.
And really, this is the most important thing to take away from all this. Writing the code for a binary search, that's the easy part. The real skill, the thing that interviewers are actually looking for, is being able to look at a complex-sounding problem like allocating books and see the simple monotonic structure that's hiding underneath. It's all about pattern recognition. So I'll just leave you with this question to chew on. Think about other famous problems like aggressive cows or the painter's partition problem, or even finding the kth smallest element in a sorted matrix. Is it possible that these are also just hiding a search for the optimal answer? Because once you start looking for this pattern, you'll be amazed at just how often you find it.